This is Lab 2, Motion of a Falling Object. In this lab, I was tasked in capturing experimental data of an object falling vertically from rest and compare it to a computational model with and without drag force. The fundamental laws associated with free fall includes Newton's first and second law. Newton's second law includes the summation of forces with acceleration involved, where the acceleration of objects is proportional to the forces acting upon it. Newton's first law involves a zero net force, which is achieved when terminal velocity is reached. The forces acting are gravity and drag force, with velocity and position examined with drag is and isn't involved. Drag force counters gravity and leads to an eventual state of equilibrium where terminal velocity, also known as maximum velocity, is reached. For my experimental data, I dropped a shuttlecock from rest. The video starts before I drop it to account for a zero initial velocity as well as a zero initial position. The mass of my system is 0.005 kilograms. The displacement for my tracker data in the y direction is negative 1.738 meters, which is important for calculating the constant proportionality B for drag force. The total time of the shuttlecock falling is 0.667 seconds. Looking at the computational model for drag force, I used my initial conditions from my tracker data. The total net force was drag force plus weight, and I used Newton's second law equation, final velocity equals initial velocity plus net force over mass times the change in time, to find my final velocity, which I then used to calculate the final position with the equation final position equals initial position plus velocity times change in time. The errors show that terminal velocity was not reached, as the system did not fall for long enough for equilibrium to be reached. To find the constant of proportionality, I used trial and error until I got 0.002. This allows for the final position to line up with the final position on my experimental data. For an experimental model without drag force, the net force includes only weight, and this leads for the final position to be overestimated as the system continues to accelerate for a longer period of time before terminal velocity is reached. The system has unbalanced forces acting. Looking at the position data for the experimental and computational models, the model with drag force included lines up with the experimental data because of the use of the constant proportionality to achieve the same final position. Whereas for the model including only weight, the terminal velocity will be larger for that computational model as it accelerates longer, and thus its final position is overestimated. Looking at which model reaches terminal velocity using the velocity time graphs is easy to see which one reaches terminal velocity. Terminal velocity is reached when the object is not accelerating anymore and is dependent upon the mass and shape of an object. The forces are balanced at that point. If only weight is taken into account, the system accelerates longer. When both drag and weight are considered, forces will eventually become balanced and acceleration will no longer occur and the terminal velocity will be reached. Looking at the slope without drag, which includes only the weight force, it is a straight line which shows that the constant acceleration due to gravity over time continues. Whereas with the slope with drag force included, it is decelerating and heading towards terminal velocity, but it is not falling for a long enough time for the terminal velocity to truly be reached. Is there a difference in terminal velocity if the object is thrown instead of allowed to fall freely from rest? The answer is no. The forces will still balance out. With attempting to capture data for this, there was more room for error, as throwing my system down resulted in the system not falling vertically the whole time. For this data to be more accurate, it would have been more important to throw the system from a higher position than simply doing what I did for the free fall data. In conclusion, this lab looked at the difference in final position and final velocity of an object in free fall with and without drag force considered. The terminal velocity is reached faster when drag force is involved. When terminal velocity is reached, the summation of forces is balanced. Before terminal velocity is reached, Newton's second law is used to find the final position, but once the terminal velocity is reached, there is no net force acting, and Newton's first law of motion comes into play, where the velocity is constant and the object stays in uniform motion until it hits the ground. For all the data, terminal velocity was not reached as the system did not fall for a long enough period of time.